Hello everyone. The topic of my presentation is automatic generation of spatial tactile effects by analyzing cross-modality features in a video. I'm Kai from ShapeLab, Stanford University. Imagine you are watching a video, for example, a car racing game like the following one. It will be a much more immersive user experience if you could really feel the bumpings of the car. People have been working on haptics for some time to provide 4D movie experience which adds physical effects to the original audiovisual content. Researchers have demonstrated that vibrotactile displays as the typical haptic devices can be used to provide physical sensations for 4D movie experience by building various platforms including gloves, blankets, and jackets. It's essential to provide meaningful tactile effects to vibrotactile displays. Many methods have been developed to author tactile effects. Manual authoring is a very common method. However, this method is laborious, since it cannot process vast amounts of information. Tactile effects can also be translated from inertial sensors. However, this method requires extra equipment. Therefore, it cannot be applied to many daily application scenarios. Researchers also translate tactile effects from audio or visual content of a video. However, these methods can only process features from a single modality, thus the performance is also limited. By analyzing the literature, we believe the following design goals are important for tactile content authoring methods. First, it should be low-cost so a broad audience can access the tactile content. It should be compatible with vast amount of information we can obtain. It should also have high accuracy. To achieve the above design goals, we developed our method. Our method is automatic, therefore it's not laborious, thus having good affordability. Our method can translate tactile effects from a video, thus it's compatible with rich video content online. Our method uses both the visual and audio features of a video. This is very similar to the way a haptic designer creates tactile content. Therefore, different from previous work which only uses single modality, our method have high accuracy. Here is an overview of what we have done in this project. We developed framework to map audiovisual content to the distribution and intensities of the spatial tactile effects. We built vibrotactile display to demonstrate the generated tactile stimuli. We conducted a user study to evaluate the generated tactile stimuli. The framework we have built to generate the spatial tactile effects is as the following. The audiovisual content is separated into visual content and audio content. Both the visual content and audio content is used to calculate the spatial distribution of the tactile stimuli and the intensity of the tactile stimuli. Next, I will talk about more details of the framework we have built. The audiovisual content is first separated into visual content and audio content as I mentioned above. Next, we use both the visual content and the audio content to separate diegetic audio from the audio content. Diegetic audio comes from on-screen sounding sources, for example, engine sound from a car racing game. Non-diegetic audio comes from off-screen sounding sources, for example, narrator's voice in a car racing game. Since translating non-diegetic audio into spatial tactile effects can be distracting, we discard the non-diegetic audio from the audio content. The visual content and the separated diegetic audio is used to determine the spatial distribution of the tactile effects. The intensity of the tactile effects is calculated by the intensity of the diegetic audio. By combining the spatial distribution of the tactile effects and the intensity of the tactile effects, we obtain the spatial tactile mapping. Next, I will talk about how we achieve each part of the framework. I will first talk about how we separate the diegetic audio. Separating multiple sounding sources is a well-studied field in the computer vision community. Among all the prior works, we found Owen's et al.'s work most relevant to our requirements. Although their work mainly focused on separating on-screen narrator's voice from off-screen narrator's voice, we found it also effective to remove off-screen narrator's voice from different sounding objects on screen. Therefore, we adapt their model as part of our framework. Then, after we separate the diegetic audio from the audio content, I will talk about how we use both the visual content and the diegetic audio to create the spatial distribution of tactile effects. From our empirical test, we find that in order to increase the user video viewing experience, it's very important to match the spatial distribution of the tactile effects with the location of the sounding sources in the video. Therefore, it's very important to locate the sounding sources in the scene. Since sound source localization is another well-studied field in the computer vision community, we didn't reinvent the wheel, but modified the model developed by Tian et al. And used it in our framework. Here are the details of the sound source localization model we used. Different from Tian et al.'s work, which uses 1-second segment of the visual content as the input. We changed the neural network so it can process each frame of the visual content. This helps to increase the dynamic response of the model. The audio signals are sent to the neural network as 1-second segment. The generated sound source localization heat map is shown on the right. It's a probability distribution heat map. The region that has a higher chance to be the sounding source is highlighted. The advantage of our model is that it can identify a smaller region as the sounding source. As we can see from the generated heat map, the model successfully identified the engine part of the car as the sounding source rather than the entire car. This advantage helps to increase the accuracy of the spatial distribution of the generated tactile stimuli. After I explained how we calculate the spatial distribution of the tactile effects, I will introduce how we calculate the intensity of the tactile effects and combine the spatial distribution and the intensity of the tactile effects to get the spatial tactile mapping. Our empirical tests show that when translating the diegetic audio signals to the tactile effects, maintaining the overall waveform will help the synchronization between the tactile effects and the audio signals, which will improve the user experience. Therefore, we use the running sum method in the translation. Since the Vibrotactile display we use has a resolution of 3 by 3, and the sound source localization heat maps we obtained in the previous steps has some noise, we built a pipeline to process it. The pipeline includes contrast stretching, downsampling, moving average, and thresholding. Finally, the haptic signal is calculated by modulating the spatial distribution of the tactile effects by the intensities. At this point, I have talked about every part of the framework we have built to automatically generate the spatial tactile effects. To demonstrate the performance of our framework, we built the following tactile rendering hardware. A Vibrotactile display was built using a chair cushion with an array of 3 by 3 haptic actuators. A control system was developed to send the tactile effects. After constructing the entire system, we conducted a user study to evaluate the generated tactile effects. In the user study, users sat against the chair cushion on the back with the Vibrotactile display on it. Audio-visual content was played on the table in front of the user. We recruited 20 participants in the user study. We designed 7 questions for the user study. The first 4 questions were to evaluate the quality of user experience, while the last 3 questions were tactile-related questions. All of the questions came from the following reference paper, which investigated a similar scenario as our paper. The independent variable in the user study is the tactile stimuli. The videos can be plain videos without any tactile effects, or videos with tactile effects generated by the salience-driven method or by our cross-modality method. Spatial tactile effects are usually decided by the number of audio-visual events in the video and the parameters of the objects in the scene, for example, number, size, and motion of the objects. We used 8 videos in the user study to cover different combinations of these factors. Here are the aggregated results for all the 8 videos we used in the user study. We can see that for all the 7 questions, our method significantly outperforms the salience-driven method. Although our method was a little bit worse than the plain videos for distraction, For the other three quality of experience questions, our method also significantly outperformed the plan videos. Next, I will talk about some representative video examples we used in the user study. The flying airplane example mainly evaluated the method's ability to track fast-moving objects in the scene. From the results, we can see that our method and the sequence-driven method had similar performance in this scenario. In the barking dog example, there are multiple audiovisual events happening in the scene. It's important to use both the visual and the audio signals so that the tactile effects can be synchronized with the barkings of the dog. Therefore, from the results, we can observe that our method significantly outperforms the sequence-driven method for all of the four quality of experience questions. The streetcars example showed one of the limitations of our current method. If there are multiple sounding sources in the scene, our method will be confused which one is the real sounding source. Therefore, from the results, we can observe that the sequence-driven method significantly outperforms our method in spatially matching the tactile effects with the movie. Following are the takeaways from the user study. Our method and the sequence-driven method obtained comparable results for spatially tracking moving objects in some examples. However, our method was more effective in temporally synchronizing tactile effects to the examples. Our method provides a better audiovisual experience compared with plan videos and the sequence-driven method. The following are the conclusions of this project. The goal of this project is to create tactile content authoring method that meets the design goals we mentioned in the introduction part. To achieve this design goal, we developed an automatic tactile stimuli generation method by analyzing cross-modality features in a video. The main findings of this project are the following. Spatial tactile stimuli can be translated from audiovisual features in a video by an end-to-end framework. Cross-modality-based generation method provides a better quality of experience than the plan videos and the sequence-driven method in our user study. Our current method still has some limitations that should be resolved by future work. First of all, our model can only identify 28 event classes in the scene. This limitation can potentially be resolved by training the model with more data in the future. As we mentioned in the user study examples, our method got confused when there are multiple sounding sources in the scene. Using spatial audio signals can potentially mitigate this limitation in the future. Our current project uses a Vibrotactile display with 3:3 resolution. Demonstrating the framework with a higher resolution Vibrotactile display will be a meaningful future work. This is the end of this presentation. Thank you for your attention.